What if everything we thought we knew about the universe was just the tip of an unimaginable cosmic iceberg? Picture this: every time you gaze up at the night sky, you're not just looking at distant stars. You're staring into a vast, dynamic tapestry of mysteries that defy our most fundamental assumptions about reality. The universe isn't just expanding, it's unfolding in ways that leave even the brightest minds in awe. Welcome to a journey through 38 insights into the architecture of the cosmos, a revised understanding where we'll peel back the layers of the cosmos to reveal a reality far more bizarre and beautiful than textbooks ever dared to suggest. Think about the last time you felt that spine-tingling sense of wonder, the kind that makes you stop and question everything. That's the feeling we're chasing today. Because hidden in the darkness between stars, woven into the fabric of space itself, are clues to a cosmic blueprint we're only beginning to decipher. Dark matter isn't just some placeholder in equations. It's the invisible scaffolding holding galaxies together. The cosmic web isn't a metaphor. It's a sprawling, living network of energy and matter stretching across billions of light years. And here's the kicker: every discovery we make doesn't just add to our knowledge. It shatters old paradigms and forces us to rewrite the rules. So why does this matter to you? Because understanding the cosmos isn't just about distant galaxies or abstract physics. It's about realizing that we're part of something grander, a story still being written. Each of these 38 insights is a thread in that story, pulling us deeper into questions about where we came from, what's really out there, and how the universe engineers its own magnificence. This isn't just science, it's a front-row seat to the greatest show in existence. So buckle up. By the end of this journey, the night sky will never look the same to you again. The idea of empty space is one of humanity's oldest illusions. We look up at the night sky and see vast stretches of darkness, assuming it's just nothing. But the truth is far stranger. Imagine a cosmic ocean, its surface seemingly calm, until you peer closer and realize it's teeming with invisible waves, particles flickering in and out of existence so fast they defy detection. This is the quantum foam, a hidden layer of reality where empty space crackles with energy. Scientists call it vacuum energy, and it's not some abstract theory. It's measurable, real, and might hold the key to one of the universe's greatest mysteries, dark energy. Here's why this matters. Every cubic centimeter of so-called empty space isn't empty at all. It's a seething dance of virtual particles, pairs of matter and antimatter that appear and vanish in fractions of a second. These quantum fluctuations aren't just random noise. They generate energy enough to potentially push galaxies apart at an ever-increasing rate. That's the leading hypothesis behind dark energy, the mysterious force accelerating the universe's expansion. Think about it: the very fabric of space itself, once thought to be a passive stage, is actually an active player in cosmic evolution. The implications are staggering. If vacuum energy truly drives cosmic acceleration, it means our universe isn't just expanding, it's being rewritten from the ground up. This isn't just about distant galaxies, it's about redefining what space even means. For centuries, we've treated the void as a backdrop, a static canvas. Now we're realizing it's more like a living, breathing entity, humming with potential energy. And here's the wildest part: the energy density of this quantum foam, if calculated naively, should be unimaginably larger than what we observe. That discrepancy tells us something fundamental is missing in our understanding. So what does this mean for our place in the cosmos? It shatters the illusion of separation. You, the air you breathe, the screen in front of you, all of it is connected by this invisible, dynamic medium. The space between stars isn't a void, it's a reservoir of untapped energy and mystery. And as we peel back these layers, we're not just uncovering new physics. We're learning that reality is far more intricate, more alive than we ever dreamed. The universe doesn't do empty. It thrives on hidden complexity, and we're just beginning to glimpse its depths. Dark matter is the universe's greatest ghost story, an invisible force we can't see, touch, or detect directly, yet its fingerprints are everywhere. Picture a sculptor shaping clay without ever touching it, guiding galaxies into swirling spirals and clusters with nothing but gravity. That's dark matter's paradox. It's everywhere, holding the cosmos together, yet it refuses to reveal itself. Recent supercomputer simulations paint a breathtaking picture, a vast, delicate web of dark matter filaments stretching across the universe, with galaxies clinging to them like dewdrops on a spider's silk. This hidden architecture isn't just background noise, it's the blueprint of existence itself. But here's where the mystery deepens. After decades of searching, we still don't know what dark matter actually is. Some physicists argue it's made of undiscovered particles, relics from the universe's earliest moments, streaming through you right now without a trace. Others wonder if we've been asking the wrong question altogether. What if dark matter isn't a thing, but a sign that gravity itself works differently on cosmic scales? Imagine rewriting the rules of physics because the universe left us a clue in the way galaxies spin. The stakes couldn't be higher. If dark matter is a particle, it would open doors to an entirely new realm of physics, a shadow universe hiding in plain sight. Experiments deep underground, in abandoned mines and mountaintop observatories, hunt for these elusive particles with detectors so sensitive they can hear the whisper of a single atomic nucleus recoiling. Yet so far, silence. That absence is its own kind of clue, pushing scientists to rethink everything. And then there's the cosmic web. Those simulations reveal something hauntingly beautiful. Dark matter doesn't just clump randomly. It forms an intricate lattice, a scaffolding where ordinary matter, the stuff of stars, planets, and us collects like frosting on a cake. Without this unseen framework, galaxies would fly apart, and the universe as we know it wouldn't exist. It's humbling to realize we're riding the currents of something we can't even see. So what's next? The hunt continues, with telescopes mapping the web's structure and particle colliders probing the frontiers of known physics. Every null result, every unexpected twist in the data, forces us to dig deeper, because solving dark matter isn't just about filling a gap in our equations, it's about uncovering the hidden gears turning the cosmic machine. And when we do, the universe might just reveal itself to be stranger than we ever dared to dream. The cosmic web isn't just a structure, it's a masterpiece of fractal artistry, a pattern so vast it defies comprehension, yet so precise it echoes in the smallest corners of nature. Picture a snowflake under a microscope, its delicate branches radiating in perfect symmetry. Now zoom way out, to see galaxies strung along filaments of dark matter like pearls on an invisible necklace, weaving a web that stretches across the observable universe. This isn't coincidence, it's a clue. The same spirals in seashells, the branching of trees, the veins in a leaf, they all whisper a secret. The universe repeats itself from the quantum to the cosmic. But why? Why would galaxies billions of light years apart arrange themselves in patterns that mirror the microscopic world? The answer might lie in something deeper than gravity or dark matter, a fundamental law of organization that transcends scale. Think of it like a universal recipe. Whether you're baking a crumb or a galaxy, the same ingredients, energy, matter, and the forces that bind them create familiar shapes. Turbulent fluids, electrical discharges, even the growth of mold on a Petri dish, they all produce branching patterns eerily similar to the cosmic web. It's as if the universe has a favorite blueprint, one it uses everywhere from the tiniest cracks in drying mud to the grandest structures in existence. Here's where it gets mind-bending. Some scientists propose this isn't just a visual similarity, it's mathematical. Fractals, those infinitely complex shapes that repeat at every scale, might be coded into the fabric of reality itself. The cosmic web's filaments branch and split like lightning, each segment a smaller version of the whole. Even the distribution of galaxies follows precise ratios, matching patterns seen in everything from DNA folding to internet traffic. Could this symmetry be a fingerprint of the universe's hidden programming? The implications are staggering. If the same rules govern the very small and the unimaginably large, it suggests a cosmos far more interconnected than we ever imagined. Dark matter's gravitational pull might be the loom, but the threads, the underlying physics, could be weaving something even more profound. A universe where complexity emerges from simplicity, where chaos gives birth to order, and where the same elegant mathematics dances from quarks to quasars. So what does this mean for us? It's more than just a pretty pattern. It's a roadmap. By studying the cosmic web's fractal beauty, we might uncover the universe's operating system, the code that turns randomness into structure, energy into galaxies, and dust into life. Every time we find this pattern, from the swirl of a hurricane to the spin of a galaxy, we're glimpsing the same cosmic handwriting, and that's the real revelation. The universe isn't just vast. It's speaking to us in a language of shapes, waiting for us to listen. Imagine the entire Milky Way along with 100,000 other galaxies being pulled irresistibly toward some unseen cosmic giant. Not by choice, not by chance, but by a gravitational force so immense it defies explanation. This is the Great Attractor, a hidden heavyweight lurking in the darkness behind our own galaxy's dust, warping the paths of everything around it like a celestial siren. We can't see it directly, but we feel its pull, a mystery so profound it challenges everything we thought we knew about the universe's structure. For decades, astronomers mapped the motion of galaxies only to find something bizarre. A vast river of galaxies, our own included, all streaming toward the same invisible point in space. At first, they assumed it was just a dense cluster of galaxies, a supercluster perhaps, exerting extra gravity. But as observations sharpened, the numbers didn't add up. The pull was too strong, too focused. The Great Attractor wasn't just a clump of matter, it was something else entirely, something that shouldn't exist under our current understanding of physics. Here's the twist: the Great Attractor isn't even the end of the story. Beyond it lies something even larger, the Shapley supercluster, a titanic gathering of galaxies so massive it might be pulling the Great Attractor itself. It's like discovering a hidden mountain range behind what you thought was the tallest peak. But even that doesn't fully explain the anomaly. Some theorists whisper about exotic possibilities, primordial black holes left over from the Big Bang, unseen dimensions leaking gravity into our own, or even flaws in Einstein's theory of relativity itself. The irony is palpable. We live in an age where telescopes can peer back to the universe's infancy, yet our own galactic neighborhood hides one of its biggest secrets just out of sight. The Milky Way's thick disk of dust and stars blocks our view, leaving us to study the Great Attractor indirectly, like detectives reconstructing a crime scene from scattered clues. X-ray observations reveal hot gas swirling toward it, and radio telescopes map the distorted paths of galaxies caught in its grip. Every new piece of data only deepens the enigma. So what's at stake? If the Great Attractor turns out to be something beyond a supercluster, some unknown cosmic phenomenon, it could rewrite the rules of gravity, mass, and large-scale structure. Or perhaps it's a signpost pointing to even grander structures we've yet to map, a single thread in a tapestry of invisible forces shaping the universe. Either way, it's a humbling reminder, even as we unravel the cosmos' biggest mysteries, the universe always keeps a few cards close to its chest, and that's the thrill of the hunt. Every answer leads to a deeper question. Time isn't the steady, unbroken river we imagine. Einstein shattered that illusion long ago, showing how clocks tick slower near massive objects, or at high speeds time bends, stretches, and warps like taffy in the cosmic heat. But what if time isn't just flexible? What if it's not even real in the way we think? Some of the boldest theories in physics suggest time might be an emergent phenomenon, a side effect of something far more fundamental. Imagine a universe where the past, present, and future don't flow in a line but exist all at once, frozen in an eternal now. Our perception of moments slipping by could be nothing more than a trick of consciousness, like a flipbook creating motion from static pages. The idea comes from quantum gravity, where scientists grapple with unifying Einstein's relativity with the chaotic rules of the quantum world. In some of these models, time vanishes entirely from the equations. It's not a variable, it's not a dimension, it's something that arises from the interactions of timeless building blocks. Think of it like temperature. We feel it, measure it, but it's not a fundamental thing. Temperature emerges from the frenzied motion of atoms. Could time be the same, a collective illusion born from deeper, unchanging physics? Here's where it gets wild. If time isn't fundamental, then causality, the idea that causes precede effects, starts to wobble. Experiments with entangled particles already show quantum events that defy before and after. Two particles can influence each other instantaneously across vast distances, as if time isn't governing their connection. And in black holes, where gravity crushes space-time into a singularity, equations suggest time itself might cease to exist. Not slow down, not stop, disappear. So what does this mean for us? If time is emergent, our entire experience of reality, memory, aging, even free will might need rethinking. The universe could be more like a block of marble, with every moment already carved into it, and our brains simply moving through it like a spotlight, illuminating one slice at a time. Philosophers call this the block universe theory, and it's not just speculation. The math supports it. Even our language struggles to describe it. We say time passes, but if time isn't flowing, what's doing the passing? The implications ripple outward. If the future is just as fixed as the past, does choice even exist? Or is our sense of agency another emergent property, a story we tell ourselves to make sense of the timeless whole? Some physicists argue this doesn't doom us to determinism, that free will and timelessness can coexist in a way we don't yet understand. Others see it as proof that time, at its core, is a human-scale illusion, irrelevant to the universe's deepest workings. One thing's certain, the more we peel back the layers, the less time looks like a backdrop and more like a character, one that might not even be essential to the plot. Whether it's a fundamental force or a cosmic afterthought, one truth remains. Our understanding of existence is due for a rewrite, and the next revelation. It's already waiting timelessly just beyond the edge of our current knowledge. What if everything you see, touch, and experience, every star, every atom, every fleeting thought, is just an illusion? Not in some philosophical sense, but in a shockingly literal way. The holographic principle turns reality inside out, suggesting our three-dimensional world might be nothing more than a cosmic mirage, a projection of information encoded on a distant two-dimensional surface. Picture a movie screen where the images appear to have depth, shadows, and movement, except in this case, The screen is the edge of the observable universe, and the movie is everything that exists. This isn't science fiction. The math checks out. Black holes pose the first clue. When matter falls into one, the information it carries doesn't just vanish. Quantum mechanics insists information must be preserved, even if it's scrambled beyond recognition. But here's the paradox. Black holes have entropy, a measure of information, proportional not to their volume, but to their surface area. It's as if all the data about what's inside gets compressed onto the event horizon skin, like a cosmic hard drive. Extend that idea to the entire universe, and suddenly, the holographic principle doesn't seem so far-fetched. Think of it like a smartphone video. The screen displays a 3D world, but the data is stored as flat pixels. The universe might work the same way. Our perception of depth, texture, and time could be an elaborate rendering of data written on a boundary we can't see. String theorists take it further, suggesting the fabric of space itself emerges from entangled quantum bits on this distant surface. Even gravity, the force that sculpts galaxies, might not be fundamental, just a side effect of how this cosmic code interacts. But how could a flat surface encode something as rich as reality? Imagine painting a masterpiece, not with brushes, but with relationships. Every particle, every force, every vibration is just a node in an unimaginably complex network of information. The 3D world we experience is the emergent pattern, like the shimmering surface of a lake reflecting sunlight. The ripples aren't the light, they're the interaction. Similarly, our reality might be the dance of data, not the data itself. The implications are dizzying. If the holographic principle holds, it could bridge the gap between quantum mechanics and gravity, the holy grail of modern physics. Quantum weirdness, with its spooky action at a distance, might just be the glitches in the projection, and dark energy, perhaps a mismatch in how the cosmic code scales. Even consciousness, that ineffable sense of being, might be part of the rendering process, like a subroutine in the universe's operating system. Skeptics argue it's untestable, but experiments are underway. Some teams are hunting for pixelation in spacetime itself, tiny, Planck-scale fuzziness that would betray the illusion. Others are simulating holographic universes in supercomputers, watching to see if 3D physics emerges from 2D rules. And if they succeed, it would mean the cosmos is the ultimate magic trick, a grand deception where every law, every constant, every star in the sky is just ink on the surface of something infinitely stranger. Here's the real mind bender. If the holographic principle is true, then you right now, reading this, are both the projection and the projector. The universe isn't just out there. It's a feedback loop, a self-referential code where observation and creation blur. The boundary isn't a wall, it's a mirror, and somewhere in the interplay of light and information, reality keeps rewriting itself. Black holes have long been painted as the universe's ultimate villains, cosmic vacuum cleaners, sucking in everything that strays too close. But what if we've had it all wrong? These gravitational behemoths might not be the end of the story. They could be the beginning. Imagine a black hole not as a pit of oblivion, but as a cosmic alchemist, transforming matter and energy in ways that shape galaxies, ignite stars, and possibly even hatch entirely new universes. At the heart of every galaxy, including our own Milky Way, lurks a supermassive black hole, a silent titan weighing millions or even billions of times the mass of our Sun. Far from being inert, these monsters are dynamic engines. As they devour gas and dust, they spew out jets of high-energy particles that can stretch for thousands of light years, heating interstellar material and triggering the birth of new stars. It's a paradox, destruction giving rise to creation. Without black holes stirring the cosmic pot, galaxies might never have formed the intricate spirals and clusters we see today. But the real twist comes when we peer into the black hole's deepest mystery, the singularity. At its core, gravity becomes so intense that space-time curves infinitely, and the laws of physics as we know them break down. Some theories suggest this isn't just a dead end. It could be a gateway, the mind-bending mathematics of loop quantum gravity and string theory hint that a singularity might not crush matter into nothingness, it could rebound, birthing an entirely new space-time bubble. A baby universe with its own unique physics, expanding unseen within the belly of the black hole that spawned it. Think of it like a cosmic Russian nesting doll. Our universe could be one of countless others, each born from a black hole in a parent cosmos. The idea isn't as far-fetched as it sounds. The equations show that the conditions inside a black hole's collapse could mirror those of the Big Bang, an explosion of spacetime from an ultra-dense state. If true, it means every black hole might be a universe factory, churning out new realities with laws slightly tweaked from our own. Some might have stronger gravity, others weaker. Some could be rich with life, others barren. The implications ripple outward. If black holes can create universes, then our own existence might trace back to one. The Big Bang could have been the birth cry of a new spacetime, forged in the collapse of a black hole from another reality. This isn't just poetic speculation, it's testable. Scientists are searching for subtle fingerprints in the cosmic microwave background, the afterglow of the Big Bang, that might reveal if our universe was shaped by a parent black hole's physics. Others are simulating black hole collapses in supercomputers, watching for signs of universe formation. And here's the kicker: if black holes are cosmic wombs, then the cycle could be eternal. Universes giving rise to black holes, which in turn spawn new universes in an endless dance of creation. It reshapes how we see our place in the cosmos, not as a one-time accident, but as part of an infinite lineage. The next time you gaze at the night sky, consider this. Somewhere out there, a black hole might be cradling a newborn universe of its own. And in some other reality, another version of you could be looking back, wondering the same thing. The idea that our universe might be just one page in an infinite cosmic library sounds like science fiction until you look at the math. The multiverse hypothesis isn't some wild guess. It emerges naturally from two of physics' most robust theories, cosmic inflation and quantum mechanics. Picture the Big Bang not as a one-time explosion, but as a never-ending firework display. Inflation theory suggests our observable universe is just one bubble in a frothing sea of spacetime, where new universes constantly bud off, each with its own unique physics. Some might have stronger gravity, others might lack electromagnetism entirely. A few could even harbor life forms built from entirely different building blocks. But how could we ever prove something so extravagant? Scientists aren't just waving their hands, they're hunting for clues. One tantalizing possibility involves cosmic scars, anomalies in the cosmic microwave background, the afterglow of the Big Bang. If our universe ever collided with another, even gently, it might have left a faint bruise in this primordial light. Think of it like two soap bubbles bumping in a sink. The point of contact would ripple. Telescopes have already spotted odd asymmetries in the CMB, unexplained cold spots and strange alignments that some researchers argue could be multiverse fingerprints. Skeptics counter that these could just be statistical flukes, but the hunt continues. Then there's the quantum angle. Every time a particle's wave function collapses, the many worlds interpretation suggests reality branches. Your decision to read this script spawned another universe where you clicked away. While this version of the multiverse lacks the grandeur of colliding bubble universes, it's equally mind-bending. The catch: these parallel realities are forever out of reach. like shadows cast by a flame we can never touch. Critics dismiss the multiverse as untestable metaphysics, but supporters fire back with a provocative question. If inflation and quantum theory are correct, wouldn't the multiverse be the most conservative conclusion? Denying it might require inventing new physics just to keep our universe special, and specialness is something cosmology has learned to distrust. We once thought Earth was the center of the solar system, then the Milky Way was the only galaxy. Every time we assumed uniqueness, the universe humbled us. The debate cuts to the heart of science itself. Is the multiverse a thrilling prediction or a philosophical dead end? Some argue it's no different than early astronomers theorizing exoplanets before we could detect them. Others worry it's a slippery slope. If we accept realities we can't observe, where do we draw the line? For now, the multiverse remains a spectrum of ideas, from the cautiously mathematical to the wildly speculative. But here's what's undeniable. The very fact we're having this conversation proves the universe, whether alone or among infinite siblings, is far stranger than we ever imagined. Every second, trillions of ghostly particles pass straight through your body, through the ground beneath you, through the entire planet, without a single collision. These are neutrinos, nature's most elusive messengers, so ethereal they make X-rays look solid. Born in the hearts of stars, the fury of supernova, and even the decay of atoms in your own bones, neutrinos barely interact with matter at all. Yet their very aloofness makes them indispensable. They're cosmic spies, slipping past barriers light can't penetrate, carrying intel from the universe's most violent and hidden corners. Take the Sun, for example. Solar neutrinos stream toward Earth at nearly the speed of light, offering a direct window into the fusion reactions powering our star. But when scientists first tried counting them in the 1960s, they hit a snag. Only a third of the expected neutrinos showed up. This solar neutrino problem baffled physicists for decades until they realized neutrinos weren't missing. They were shape-shifting. Neutrinos come in three types or flavors: electron, muon, and tau. As they travel, they oscillate between these flavors like a chameleon cycling through colors. That discovery proved neutrinos have mass, however minuscule, upending the Standard Model's prediction that they should be massless. Here's why that's revolutionary. The Standard Model is particle physics' crown jewel, a framework so precise it's predicted countless phenomena, but neutrino oscillations expose its cracks. If neutrinos have mass, even a whisper of it, then the model is incomplete. Some theories suggest neutrinos might be Majorana particles, a rare breed that are their own antimatter twins. If true, it could explain why the universe favors matter over antimatter, solving one of cosmology's biggest riddles: why we exist at all. Neutrinos also serve as cosmic archaeologists. When a star explodes as a supernova, 99% of its energy escapes as neutrinos, arriving hours before the light does. In 1987, detectors on Earth caught neutrinos from a supernova in the Large Magellanic Cloud, marking the first time we'd observed particles from beyond our solar system. Today, scientists are building even more sensitive detectors, like Japan's Super Kamiokande, a tank filled with 50,000 tons of ultra-pure water, lined with sensors waiting for the faintest neutrino flash. These observatories aren't just hunting supernova, they're listening for neutrinos from the universe's first seconds, relics of the Big Bang itself. But the real magic lies in what we haven't seen yet. Some neutrinos arrive with energies millions of times higher than those from our Sun, and we've traced a handful back to distant blazars, supermassive black holes spearing jets of particles toward Earth. Yet many ultra-high-energy neutrinos have no obvious source, hinting at phenomena we've yet to imagine. There's even speculation about sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity, possibly linked to dark matter. So why do these phantoms captivate physicists? Because neutrinos don't play by the rules. Every time we think we've pinned them down, they reveal a new trick, forcing us to rewrite the textbooks. They're both particle and paradox, whispering secrets about the universe's birth, the fabric of reality, and the laws we thought we knew. In a cosmos full of mysteries, neutrinos might just be the most tantalizing clue of all. Quantum entanglement is the universe's ultimate magic trick. Particles born together or interacting briefly become bound in an invisible embrace, their fates intertwined no matter how far apart they drift. Measure one and its partner instantly responds as if space and time don't exist between them. Einstein famously called this spooky action at a distance, dismissing it as impossible. Yet experiment after experiment confirms it's real, but here's the real mystery. What if this bizarre phenomenon isn't just a quirk of tiny particles? What if it's the glue holding spacetime itself together? Picture the cosmos as a vast, shimmering tapestry. Every thread, every galaxy, every star is stitched into place by an unseen network of quantum connections. This isn't just poetic imagery. Cutting-edge theories in quantum gravity suggest entanglement might be the secret ingredient that gives rise to space and even time. Think of it like a cosmic game of connect the dots, where the dots are particles and the lines between them aren't just lines, they're the fabric of reality. When two particles entangle, they don't just share information, they might literally create the space between them. The math is staggering. In some models, the more entangled two regions of space are, the closer they behave geometrically. Pull them apart, and the entanglement stretches like invisible taffy, maintaining their connection. This could explain how black holes, those cosmic paradoxes, preserve information despite swallowing it beyond an event horizon. The entanglement of particles near the edge might encode what falls inside. It's as if the universe has a backup drive written in quantum links we're only beginning to decode. And then there's the cosmic scale. The early universe was a hot, dense soup of particles, all entangled in a primordial quantum dance. As space expanded, those connections didn't just vanish, they stretched, thinned, and perhaps wove the large-scale structure we see today. The cosmic web, with its filaments and voids, might be the fossilized imprint of ancient entanglement. Even dark matter's elusive influence could be part of this quantum scaffolding, its gravity emerging from deeper, invisible bonds. But how do we test such a wild idea? Scientists are already on the hunt. Some study entanglement in lab-grown black hole analogs, watching how quantum links behave under extreme conditions. Others analyze the cosmic microwave background for patterns that might reveal an entangled infancy. And then there's the holographic principle, which suggests entanglement entropy, a measure of quantum connectedness, might literally define how spacetime curves. The implications are profound. If entanglement builds space, then the universe isn't just a collection of objects inside a container. It's a dynamic network of relationships. Particles aren't just things, they're knots in a quantum web, their existence defined by connections. This flips our understanding of reality on its head. Distance, separation, even individuality might be illusions, emergent properties of something far deeper. So next time you look up at the night sky, remember, those stars aren't just points of light. They're nodes in a cosmic conversation, whispering to each other across the void via threads of quantum entanglement. And somewhere in that silent dialogue might lie the answer to the oldest question of all: what is the universe truly made of? The silence of the cosmos is deafening. With billions of galaxies, each hosting billions of stars and countless planets, the universe should be buzzing with life. Yet, as far as we can tell, it's just quiet. This is the Fermi Paradox in a nutshell, the glaring contradiction between the high probability of extraterrestrial civilizations and the utter lack of evidence for them. But what if we've been asking the wrong questions? What if the answers aren't about them, but about us and the nature of life itself? One unsettling possibility is that advanced civilizations tend to self-destruct before they can colonize the stars. Imagine a species like ours, but a few centuries ahead, mastering fusion energy, cracking genetic code, and developing artificial intelligence. Now picture the flip side: nuclear war, runaway climate change, or AI turning hostile. The window between gaining the power to shape a planet and the wisdom to wield it responsibly might be perilously narrow. This great filter theory suggests that most civilizations hit a wall, whether through war, ecological collapse, or technological hubris. The eerie silence could be a cosmic graveyard, filled with civilizations that blinked out before they could say hello. But let's flip the script. What if the problem isn't extinction, but evolution? Some theorists argue that sufficiently advanced civilizations might transcend physical form, uploading their consciousness into digital realms or merging with machines. In this scenario, the universe isn't empty. It's just inhabited by entities so far beyond our comprehension that they're invisible to us. They might not build radio towers or spaceships. They could exist as pure information, woven into the fabric of spacetime itself. We wouldn't recognize their signals because we're still thinking in terms of things, not patterns. Then there's the zoo hypothesis, the idea that Earth is deliberately left undisturbed, a cosmic nature preserve where younger species like ours can develop without interference. It's a comforting thought, but it raises a chilling question: who's running the zoo, and what happens when we're advanced enough to notice the keepers? But here's the most humbling possibility of all. What if we truly are alone? The universe might be lush with planets, but life, especially intelligent life, could be a freak accident, a 1 in a trillion fluke. The chemical steps from amino acids to self-aware beings might be so improbable that Earth is the only place it's ever happened. This isn't just a scientific question, it's existential. If we're the universe's only way of knowing itself, then every choice we make carries cosmic weight. The Fermi Paradox isn't just about aliens, it's a mirror forcing us to confront who we are and what we might become. Are we destined to fade into the silence, or will we one day add our voice to the cosmic chorus? The answer isn't written in the stars, it's being written by us right now. What if the universe isn't the ultimate reality, but an elaborate simulation running on some advanced civilization supercomputer? The simulation argument isn't just sci-fi speculation, it's a serious hypothesis debated by philosophers and physicists alike, rooted in observable trends. Think about it, within just a century, we've gone from room-sized computers to devices in our pockets that simulate entire worlds. Now project that progress forward 1,000 years or 1,000,000. If civilizations keep advancing, wouldn't they eventually create simulations indistinguishable from reality? And if they could, wouldn't they run countless ones, making simulated minds vastly outnumber biological ones? Statistically, the odds tilt heavily toward us being in one of those simulations. But this isn't just about numbers. The idea resonates with quirks in our own physics. Take the speed of light. Why is it capped at 300,000 kilometers per second? In a simulation, processing limits might impose such constraints to prevent system overload. Quantum mechanics gets even weirder. Particles only settle into definite states when observed, like a video game rendering graphics only where the player looks. Even mathematical constants appear suspiciously fine-tuned, as if dialed in by a programmer to allow complex structures like galaxies and life to exist. Coincidence, maybe, but the simulation hypothesis offers a provocative explanation. the implications ripple into philosophy. If we're simulated, is free will an illusion or just advanced code predicting our choices? Some argue that even in a simulation, consciousness could be real like characters in a novel who feel authentic despite being written. Others counter that creators might intervene, tweaking events like game developers patching glitches. This raises eerie possibilities. Historical anomalies, déjà vu, even UFO sightings could be artifacts of the simulation bugs or intentional adjustments by higher-level users. Critics dismiss it as unfalsifiable, but scientists aren't giving up. Some propose testing for pixelation in spacetime at Planck scale, tiny irregularities that might betray the simulation's resolution. Others suggest hunting for computational shortcuts, places where the universe approximates complex calculations to save processing power, like a video game lowering detail in distant scenery. So far, no smoking gun, but absence of evidence isn't evidence of absence. Here's the twist: even if we prove we're in a simulation, it changes nothing about our lived experience. Love, pain, curiosity, they'd still feel real. The simulation argument isn't a threat to meaning, it's a mirror. Whether we're base reality or lines of code, the questions remain: who are we? Why are we here? And if this is a simulation, what's waiting outside it? The answer might be forever out of reach, or it might be the next great frontier of human discovery. Either way, the universe just got a lot more interesting. We've been told the universe began with a bang, a single, explosive moment where space, time, and matter burst into existence. But what if that's only half the story? The Big Bang Theory has dominated cosmology for decades, yet cracks are appearing in its foundation, revealing tantalizing alternatives. Imagine a universe with no true beginning or end, an eternal cycle of expansion and contraction, like a cosmic lung breathing in and out. This is the heart of the Big Bounce theory, where each big crunch births a new universe, eternally recycling matter and energy. The math is startlingly elegant. Instead of a singularity, a point of infinite density where physics breaks down, the bounce posits a quantum bridge, where gravity reverses collapse into rebirth. Then there's the cyclic model, where universes collide in higher dimensional space, triggering new bangs like dominoes falling in an endless chain. Picture two sheets of paper, each a universe floating parallel in a fifth dimension. When they touch, the energy ignites a new expansion. This isn't just poetic imagery. String theory provides the framework, suggesting our three-dimensional world might be a membrane floating in a vast bulk of unseen dimensions. These collisions could leave scars, patterns in the cosmic microwave background that telescopes are now hunting for. But the boldest challenge comes from the steady-state theory's spiritual successor, the idea of a quiescent universe that never truly began. In this view, the Big Bang wasn't a creation event but a phase transition, like water freezing into ice. The universe might have always existed in a form we don't yet recognize, with time stretching infinitely in both directions. Quantum fluctuations could spontaneously generate matter, balancing cosmic expansion without a singular starting point. The implications are staggering. If the Big Bang wasn't the beginning, then causality, the chain of cause and effect, might unravel. Did time even have a first tick? Could information from a previous universe leak into ours like echoes in a cosmic canyon? Some models suggest black holes from a prior cycle might persist, carrying forward remnants of a forgotten cosmos. Others propose that the constants of nature, the speed of light, the strength of gravity might subtly shift between cycles, explaining why our universe seems improbably fine-tuned for life. Critics argue these theories stretch credulity, but they solve puzzles the Big Bang can't. Why is the universe so uniform on large scales? Inflation patches the answer. but a cyclic cosmos naturally smooths itself over eons. And the infamous singularity, a bounce or collision erases it entirely, keeping physics intact. Even entropy, the universe's apparent slide toward disorder, might reset in each cycle, like shuffling a deck of cards back to order. The deepest question isn't which model is right, it's what beginning even means. We're like ants trying to map a mountain by crawling up one side. Whether the cosmos is one act in an infinite play or a solo performance with no encore, one truth remains: the universe is far more dynamic, more resilient, and more mysterious than we ever dared to dream. And that's the real revelation, not how it started, but how much we've yet to discover. Dark energy isn't just another mystery, it's the universe's greatest plot twist. Picture a car rolling downhill, but instead of slowing, it inexplicably accelerates, defying every law of physics you know. That's exactly what's happening to our cosmos. In the late 1990s, astronomers made a jaw-dropping discovery. The expansion of the universe isn't just continuing, it's speeding up. Galaxies aren't drifting apart, they're being flung away from each other as if space itself is stretching faster and faster. And the culprit, a phantom force we've named dark energy, an invisible presence making up a staggering 68% of everything in existence. But what is it? The leading theory points to the cosmological constant, an energy woven into the very fabric of space. Think of it like a hidden tax on the universe, where every cubic centimeter of emptiness carries a tiny charge pushing outward. Einstein actually predicted this concept, then famously dismissed it as his greatest blunder. Yet here we are, a century later, realizing he might have been right all along. But there's a catch. The energy density we observe is 100 orders of magnitude weaker than what quantum theory suggests it should be. It's like expecting a hurricane and feeling only a faint breeze. This discrepancy is so colossal, it hints that we're missing something fundamental. Alternative theories venture into wilder territory. Some suggest dark energy isn't constant at all. It could be a dynamic field, evolving over time like an invisible fifth force. Others propose it's a symptom of extra dimensions leaking gravity into our reality, or even a sign that Einstein's theory of gravity needs revising on cosmic scales. Then there's the most unsettling possibility. Dark energy could be the precursor to a cosmic doomsday. If it strengthens over time, it might eventually tear apart galaxies, stars, even atoms in a catastrophic big rip. Yet amid the uncertainty, one thing is clear: dark energy holds the universe's fate in its grip. Will expansion continue forever, leaving galaxies isolated in an ever-cooling void? Could dark energy reverse course, collapsing everything back into a singularity? Or is the truth something stranger, something we haven't even imagined? Every telescope trained on distant supernova, every map of the cosmic microwave background, is a detective piecing together clues to this grand enigma. Here's the humbling part: we're cosmic latecomers. Dark energy's effects were negligible in the universe's youth, only dominating in the last few billion years, just in time for us to notice. It's as if the cosmos saved its biggest surprise for the moment we were ready to look. And that's the real lesson. The universe isn't just expanding. It's teaching us, with every accelerating galaxy, how much we still have left to learn. The cosmic microwave background is supposed to be the universe's baby picture, a nearly perfect snapshot of its infancy, uniform in every direction. But when scientists zoomed in, they found something unsettling. The data revealed strange, unexplained alignments in the radiation patterns, as if the universe had a hidden axis running through it like an invisible spine. Astronomers, with their flair for dramatic naming, called it the axis of evil, a cosmic anomaly so bizarre it threatens to upend our most basic assumptions about space and time. At first glance, the cosmic microwave background looks like random static, a snowy TV screen from the dawn of creation, but subtle temperature fluctuations within it tell a deeper story. These tiny variations, mapped in exquisite detail by satellites like Planck and WMAP, should be randomly distributed with no preferred direction. Yet when researchers analyzed the data, they kept stumbling over the same eerie pattern. The hot and cold spots weren't scattered haphazardly. They lined up along a specific plane, as if the universe had a built-in North and South Pole. Even stranger, this axis seems to align suspiciously well with our solar system's orientation, a coincidence so statistically unlikely it reeks of something deeper at work. The implications send shivers down the spine of cosmology. If the axis of evil is real and not just some fluke or measurement error, it could mean the universe isn't as isotropic as we thought. The bedrock principle of cosmology, that the cosmos looks the same in all directions on large scales, might have cracks. Some theorists suggest this could be a relic from before the Big Bang, a fingerprint of an earlier epoch imprinted on our universe like a shadow. Others whisper about cosmic strings defects in space-time left over from the universe's violent birth, tugging at the fabric of reality. And then there's the most unsettling possibility. What if it's not the universe that's weird, but us? Could some overlooked bias in our observations or instruments be fooling us into seeing patterns that aren't there? Skeptics argue the axis of evil might vanish with better data, but each new measurement only deepens the mystery. The Planck satellite, with its unprecedented precision, confirmed the anomaly. Not only do the temperature fluctuations align, but so do the polarization patterns like cosmic breadcrumbs pointing to something we don't understand. The odds of this happening by chance are astronomically low, somewhere in the neighborhood of 1 in 10,000. That's the kind of number that keeps scientists awake at night. So where does that leave us? If the axis of evil holds up, it could force a rewrite of cosmic history. Maybe inflation. The theory that the universe expanded exponentially in its first moments needs tweaking. Maybe there's a deeper layer of physics we haven't uncovered yet, a hidden symmetry or structure shaping the cosmos in ways we're only beginning to glimpse. Or maybe, just maybe, the universe is playing a trick on us, leaving clues to a puzzle we don't even know how to solve. One thing's certain, the cosmic microwave background, once thought to be the ultimate confirmation of our theories, has become the ultimate question mark. And that's the beauty of science. The moment we think we've got it all figured out, the universe hands us a new riddle. Black holes have monopolized the cosmic spotlight for decades, those greedy cosmic vacuums swallowing everything in their path. But what if they have secret twins operating in reverse? Enter white holes, the hypothetical yin to black holes' yang, where a black hole's gravity is so intense that nothing escapes, not even light. A white hole would be its cosmic opposite, a region of spacetime where matter and energy can only pour out, never to return. Picture a celestial fountain endlessly erupting, or a cosmic firework frozen mid-explosion. The math allows for such objects, but do they actually exist? The idea isn't as outlandish as it sounds. Einstein's equations, which predict black holes, also permit white holes as valid solutions, essentially black holes running backward in time. Some theorists suggest that when a black hole dies, it might not fade quietly into oblivion, but instead transform into a white hole, rebounding in a spectacular burst of energy. This quantum bounce could be the universe's way of recycling space-time, turning destruction into creation in one fell swoop. Imagine a black hole in one universe collapsing to a singularity, only to erupt as a white hole in another, a cosmic relay race where matter gets passed through a gravitational wormhole. Then there's the wilder possibility. White holes might not just be endpoints but beginnings. Some models propose that the Big Bang itself could have been a white hole event, a singularity violently spewing out matter and energy, birthing our universe in an explosive act of cosmic generosity. Instead of a mysterious singularity appearing from nothing, our universe might have emerged from the transformation of a black hole in some other reality. It's a tantalizing thought. Every black hole in our cosmos could be seeding a new universe elsewhere, with white holes as the fiery exits. But if white holes are real, where are they? One leading candidate is the mysterious gamma-ray burst, sudden, intense flashes of energy from deep space that outshine entire galaxies for brief moments. These could be white holes briefly opening up, ejecting matter before snapping shut again. Another clue might lie in fast radio bursts, those enigmatic blips of radio waves arriving from distant corners of the cosmos. Could these be white holes' faint echoes flickering in and out of existence? Skeptics argue that white holes violate the second law of thermodynamics, which dictates that entropy disorder always increases. A white hole spewing out ordered energy seems to defy that, yet others counter that if black holes can exist, their time-reversed counterparts shouldn't be dismissed outright. After all, the universe loves symmetry. Why should gravity be any different? The deeper question isn't just whether white holes exist, but what they'd mean for our understanding of reality. If confirmed, they'd rewrite the life cycle of the cosmos, turning black holes from dead ends into cosmic portals. They'd blur the line between destruction and creation, suggesting that every ending might be a beginning in disguise. And most mind-bending of all, they'd hint that our universe might not be the only one, just one link in an endless chain of births and rebirths. For now, white holes remain ghosts in the equations, mathematical phantoms waiting to be proven or disproven. But in a universe full of surprises, the idea that something so strange could exist is a reminder. Reality is always stranger than we imagine, and sometimes the most outlandish ideas are the ones that change everything. At the smallest scales imaginable, far beneath the level of atoms or even subatomic particles, the fabric of reality might not be smooth at all. Picture a calm ocean on a windless day, seemingly flat and undisturbed. But dive beneath the surface and you'll find a churning chaos of currents, bubbles, and turbulence. That's what space-time itself could be like at the quantum level. A seething, frothing foam where the very notions of here and now lose all meaning. This is quantum foam, a dizzying concept where tiny wormholes blink in and out of existence, where space and time twist into knots so tight they defy logic. The idea traces back to physicist John Wheeler, who realized that at scales a trillion times smaller than an atom, the uncertainty principle wreaks havoc on space-time itself. Energy fluctuations at this level are so violent that they warp the fabric of reality, creating temporary bubbles of distorted geometry. In one fleeting moment, a microscopic wormhole might form, bridging two distant points in space. In the next, a bubble of distorted time might emerge, where cause and effect flicker like a candle in the wind. This isn't science fiction, it's a direct consequence of marrying quantum mechanics with general relativity. The universe, it seems, is built on a foundation of chaos, but here's where it gets even wilder. Some theorists suggest this quantum foam isn't just background noise, it could be the key to traversing the cosmos. Those fleeting wormholes, if stabilized, might function as cosmic shortcuts, folding space so that two distant points touch. Imagine stepping through a doorway in your kitchen and finding yourself on the surface of Mars. The catch, these wormholes would be vanishingly small and unstable, collapsing faster than they form. To harness them, we'd need some way to prop them open, perhaps with exotic matter possessing negative energy, a substance that so far exists only in equations. Yet the implications ripple far beyond interstellar travel. Quantum foam could redefine our understanding of black holes, where space-time curvature becomes infinite. At their cores, beyond the event horizon, the foam might churn so violently that it births entirely new universes, each bubble a potential Big Bang. It might even hold clues to dark energy, with vacuum fluctuations in the foam driving the accelerating expansion of the cosmos. So why haven't we detected this foam? The scales involved are so absurdly tiny that current technology stands no chance. But some experiments are pushing the limits. By studying high-energy gamma rays from distant quasars, scientists hunt for signs that space-time isn't smooth, that photons traveling across the universe might stumble on microscopic bumps in the road, subtly altering their path. Others probe the quantum behavior of gravity itself, searching for hints that space-time is pixelated at the smallest scales. The quantum foam reminds us that reality, when examined closely, is anything but solid. It's a dynamic, writhing thing, full of possibilities we're only beginning to grasp, and if we ever unlock its secrets, the universe might just become a little smaller and a whole lot stranger. What if the thoughts in your head right now, the memories, the sense of self, aren't the product of billions of years of evolution, but a fleeting accident? A random spark of awareness flickering into existence for just a moment before vanishing back into the void. This is the chilling heart of the Boltzmann brain paradox, a thought experiment that turns our understanding of reality inside out. Named after physicist Ludwig Boltzmann, who grappled with the nature of randomness in the universe, it asks a deceptively simple question. In an infinite cosmos governed by entropy, isn't it more statistically likely for a fully formed, self-aware mind to spontaneously arise from quantum chaos than for an entire universe like ours to evolve naturally? Think of it like this: given enough time, a monkey randomly typing on a keyboard might eventually produce Shakespeare, but it's infinitely more probable that the monkey would type a single coherent sentence first. Similarly, in an eternal universe, the random jostling of particles could momentarily arrange themselves into a conscious brain complete with false memories of a past that never happened, far more easily than crafting stars, planets, and life over eons. These phantom minds, dubbed Boltzmann brains, wouldn't be attached to bodies. They'd be isolated flashes of consciousness, conjured from the void with the illusion of a lifetime's worth of experiences. And here's the kicker: if the cosmos truly lasts forever, Boltzmann brains should outnumber evolved beings like us by an unimaginable margin. So statistically speaking, are we the flukes? The paradox cuts to the core of cosmology and philosophy. If we accept that the universe tends toward disorder, as the second law of thermodynamics states, then highly ordered structures, like conscious minds, should be vanishingly rare. Yet we exist, so either we're staggeringly lucky, or our understanding of time, entropy, or the universe's boundaries is fundamentally flawed. Some physicists argue this paradox disproves the idea of an eternal, infinite cosmos, pointing to the need for a finite beginning or a cosmological constant that prevents such quantum aberrations. Others suggest Boltzmann brains are impossible because consciousness might require more than just the right arrangement of particles, perhaps an emergent property only possible in a structured, evolved universe. But the implications run deeper than physics. If Boltzmann brains are possible, how could we ever trust our own memories? That time you stubbed your toe as a child, the face of your first love, the very screen you're reading this on, none of it might be real. You could be a ghost of entropy, a momentary glitch in the cosmic code, convinced of a reality that never was. It's the ultimate existential crisis, stripping away not just meaning, but the certainty that anything exists at all. Yet there's a strange comfort in the paradox, the fact that we're debating it, that we can even conceive of such a dizzying idea, suggests our minds are wired for more than random chaos. Maybe the universe isn't infinite, maybe consciousness is rarer than we think, or maybe, just maybe, the Boltzmann brain paradox isn't a threat but a reminder. In a cosmos full of mysteries, the mere act of questioning our place in it is what makes us real. After all, a random fluctuation wouldn't wonder if it were random. It would just be, and that, in the end, might be the most compelling argument that we're something more. The universe is expanding, but what if that expansion doesn't just continue? What if it accelerates to the point of cosmic self-destruction? This is the nightmare scenario known as the Big Rip, a potential future where dark energy doesn't just nudge galaxies apart, but grows so powerful it shreds the very fabric of reality. Picture this. First, galaxy clusters are torn asunder, their gravitational bonds no match for the escalating force. Then, individual galaxies unravel, stars ripped from their orbits like grains of sand in a hurricane. Next, planetary systems disintegrate. Finally, in the last microseconds, atoms themselves are torn apart, their protons and electrons unable to withstand the overwhelming stretch of space-time. The cosmos wouldn't just fade into cold darkness, it would explode into nothingness, leaving behind a void so absolute it makes black holes seem cozy. The math behind this doomsday is as elegant as it is terrifying. Dark energy's behavior is quantified by its equation of state, a number representing its pressure-to-density ratio. If this value dips below -1, if dark energy becomes phantom energy, its strength would grow over time rather than remaining constant. Like a car with a stuck accelerator hurtling toward a cliff, the universe would reach a point of no return. Current observations put the value perilously close to this threshold, hovering around -1. The margin for error is slim, and the stakes couldn't be higher. But here's where the plot twists. The Big Rip isn't the only possible fate. Some theories suggest dark energy might weaken or even reverse, leading to a big crunch where the universe collapses back into a singularity. Others propose it could plateau, leaving galaxies isolated but intact in an eternal, lukewarm expanse. The wildest idea, dark energy might not be a force at all, but a symptom of our incomplete understanding of gravity. Modified gravity theories, like MUND, argue that what we call dark energy could just be gravity behaving strangely on cosmic scales. If true, the Big Rip might be a phantom menace, a miscalculation waiting to be corrected. Yet the most unsettling question isn't if, but when. If phantom energy is real, the countdown could already be ticking. Estimates vary wildly, from tens of billions of years to a mere few hundred million. On cosmic timescales, that's the blink of an eye. But here's the silver lining. Every moment we spend studying dark energy is a chance to rewrite the ending. Experiments like the Dark Energy Survey and future space telescopes are mapping its influence with unprecedented precision. Each new data point could be the clue that saves the universe or confirms its expiration date. The Big Rip isn't just a scientific curiosity. It's a mirror held up to our place in the cosmos. Will the universe end with a whimper, a bang, or a tear? The answer might depend on how well we can decode its deepest secrets and how fast we can learn to think beyond the physics we know. One thing's certain, in the face of such stakes, the universe has never felt more alive, more fragile, or more worth understanding. Black holes have long been cosmic enigmas, but their greatest paradox isn't their immense gravity, it's what happens to the information they swallow. According to quantum mechanics, information can never truly vanish. It might get scrambled, but it can't be erased. Yet black holes, with their insatiable appetites, seem to break this rule. Whatever falls past the event horizon appears lost forever, crushed into oblivion at the singularity. This contradiction, known as the information paradox, has haunted physicists for decades, forcing them to question whether our understanding of reality itself is flawed. Enter Stephen Hawking. In his final groundbreaking work, he proposed a tantalizing solution. Black holes might not be the ultimate shredders we thought. Instead, they could leave behind faint imprints, what he called soft hair. These aren't literal strands, but subtle patterns of zero-energy particles lingering at the event horizon, encoding traces of whatever fell inside. Think of it like cosmic graffiti, etched into the boundary of the black hole by the objects that crossed it. These quantum markings wouldn't preserve the information in any recognizable form. No one's retrieving your lost socks from a black hole, but they'd ensure the universe's ledger stays balanced. The implications ripple far beyond black holes. If information isn't destroyed, it means space-time might have a built-in backup system, a way of preserving data even in the most extreme environments. This challenges the very notion of singularities as points of infinite destruction. Instead, black holes could operate like cosmic encryptors, transforming matter into quantum code stored on their surfaces, a concept eerily reminiscent of the holographic principle. Yet the debate rages on. Some theorists argue soft hair isn't enough to resolve the paradox, pointing to firewalls, searing walls of energy at the event horizon that would vaporize anything falling in. Others explore even wilder ideas, like black holes funneling information into baby universes, or leaking it through Hawking radiation in ways we can't yet detect. The math is a battleground, with equations clashing like tectonic plates, reshaping our view of reality's fabric with each new skirmish. At its core, the information paradox isn't just about black holes. It's a proxy war for deeper questions. Is the universe deterministic, with every event traceable back to its origins? Or does quantum randomness truly erase history in places? The answer could redefine causality, entropy, even the nature of time itself. For now, black holes remain the universe's ultimate vaults, locked, mysterious, and daring us to crack their codes. And with every new theory, we're not just solving a puzzle, we're rewriting the rules of existence. The universe's infancy was a violent place, a seething cauldron of energy where space itself could have briefly folded into microscopic knots of unimaginable density. These knots, if they survived, would be primordial black holes, tiny, ancient relics born not from dying stars, but from the raw turbulence of the Big Bang itself. Unlike their stellar counterparts, these black holes could be as small as an atom or as massive as a mountain, lurking unseen throughout the cosmos. And here's the tantalizing possibility: they might be the elusive dark matter we've been chasing for decades. Imagine dark matter not as a cloud of exotic particles, but as a cosmic minefield of these primordial black holes, scattered across galaxies like invisible anchors. The math is compelling. In the first chaotic seconds after the Big Bang, regions of space slightly denser than their surroundings could have collapsed directly into black holes without ever forming stars. Some might have evaporated via Hawking radiation by now, but those heavier than 1 billion tons could still persist, drifting between stars and passing through planets like ghosts. Including Earth, you might have one in front of you right now, too small to see, yet dense enough to punch straight through the planet without leaving a trace. The beauty of this hypothesis is its economy. It solves two cosmic mysteries at once: dark matter's gravitational effects, the way it bends light around galaxies and holds clusters together, could be explained by these hidden black holes. And unlike hypothetical particles such as WIMP, which decades of experiments have failed to detect. Primordial black holes are built from known physics. No new particles required, just gravity warping space in ways we already understand. But how would we find them? The hunt is already underway. Some teams scour old photographic plates for sudden flashes, the telltale sign of a tiny black hole magnifying a distant star's light as it passes in front. Others listen for the faint echoes of black holes colliding, not in distant galaxies, but in our own cosmic backyard. Then there's the most mind-bending clue of all, the mysterious black holes detected by LIGO with masses too large for stellar collapse, yet too small for supermassive giants. Could these be primordial black holes, ancient survivors of the universe's first moments? Critics point out the gaps. If primordial black holes are everywhere, why haven't we seen more gravitational lensing events? Why don't they disrupt star clusters more visibly? Yet every objection sparks new refinements. Perhaps they're clustered in halos around galaxies, or maybe most are just outside our current detection thresholds. The debate isn't just academic. Finding even one primordial black hole would rewrite cosmic history, proving the early universe was wilder and more inventive than we ever imagined. And the implications run deeper. If these black holes exist, they're time capsules from the universe's first second, carrying clues about conditions so extreme they make the core of a supernova look tame. They could be the missing link between quantum mechanics and gravity, or even seeds for the supermassive black holes that now anchor galaxies. Most thrilling of all, they'd prove that black holes aren't just endpoints of dead stars. They're part of the universe's original blueprint, woven into the cosmos from the very beginning. The hunt for primordial black holes is more than a scientific challenge. It's a reminder that sometimes the answers we seek aren't in undiscovered particles or hidden dimensions, but in the subtle scars of a universe that's always been stranger than we guessed. And if they're out there, we're not just solving a puzzle, we're touching the shadows of creation itself. The periodic table seems like a solved puzzle: hydrogen, helium, lithium, the elements forged in the Big Bang's fiery crucible. But there's a cosmic detective story hidden in row 3, where lithium sits with a glaring inconsistency. According to our best models of nuclear fusion in the universe's first minutes, there should be about 3 times more lithium in the cosmos than what we actually observe. This isn't a minor rounding error, it's a gaping hole in our understanding of the infant universe's chemistry. Where did all that lithium go? The mystery starts with Big Bang nucleosynthesis, the process that cooked up the universe's first atomic nuclei. In those initial frenetic minutes, protons and neutrons collided to form deuterium, helium, and trace amounts of lithium and beryllium. The calculations are precise down to the last decimal, matching observed helium and deuterium levels almost perfectly. But lithium, the numbers stubbornly refuse to align. Ancient stars, which should preserve that primordial lithium like cosmic time capsules, show only a fraction of the expected amount. It's as if someone or something scooped out 2/3 of the universe's lithium supply before stars even formed. One possibility is that our models of those first nuclear reactions are incomplete. Maybe unknown particle interactions or fluctuations in the early universe's density altered lithium production. Some theorists propose actions, hypothetical particles that could have influenced nuclear fusion rates. Others suggest lithium might have been destroyed later, swallowed by hypothetical dark stars made of exotic matter or transformed through interactions with dark energy. The wildest idea, that lithium's absence points to a brief epoch of new physics, a phase transition or extra dimension that tweaked nuclear behavior before fading into obscurity. Then there's the stellar angle. Could stars themselves be the culprits, burning away primordial lithium over billions of years? Observations of young, metal-poor stars suggest otherwise they're still lithium deficient. But turbulence in stellar interiors or undiscovered mixing processes might explain how lithium gets depleted. It's a cosmic game of hide and seek, with the universe offering few clues. The implications ripple far beyond a single element. If standard particle physics can't account for missing lithium, it might hint at gaps in our understanding of fundamental forces. Or worse, it could mean the Big Bang wasn't the pristine, uniform event we've assumed. Alternative theories, like a bouncing or cyclic universe, might leave different elemental fingerprints. For now, lithium remains the universe's lost receipt, a discrepancy that refuses to be ignored. Every new observation, from the spectra of ancient stars to the subtle vibrations of the cosmic microwave background, brings us closer to solving the case. And when we do, the answer might rewrite not just the periodic table, but the very story of how everything began. That faint glow permeating the cosmos, the cosmic microwave background, is supposed to be almost perfectly uniform, a quiet echo of the Big Bang's heat. But nestled in the southern sky lies an anomaly so bizarre it defies easy explanation: the CMB cold spot. This sprawling region, spanning nearly 1 billion light-years, is significantly colder than its surroundings, as if someone pressed an icy hand against the fabric of the universe. At first glance, it might seem like a random fluctuation, a cosmic hiccup in the data, but the odds of such a deep, localized chill appearing by chance? Less than 1 in 50, so what could carve a hole in the afterglow of creation? One electrifying possibility is that we're staring at a bruise, a collision scar from a neighboring universe bumping into ours during inflation. Picture 2 soap bubbles expanding in a froth of spacetime. Where they briefly touch, their boundaries might leave an imprint. In this scenario, the cold spot could be evidence of a multiverse, a reality where our cosmos is just one bubble in an endless, frothing sea. The physics aligns eerily well. A collision would drain energy from that region of space, leaving it colder than its surroundings. It's as if the universe next door reached out and gave us a ghostly handshake. Yet skeptics aren't ready to rewrite cosmology just yet. Alternative explanations abound. The cold spot might be a supervoid, an enormous, mostly empty region of space where the lack of galaxies means less matter to subtly warm the CMB. But here's the catch: the largest known voids don't match the cold spot's scale or temperature profile. Another theory suggests cosmic texture, a hypothetical defect in spacetime structure, a knot left over from the universe's violent birth. These textures, if they exist, could create temperature variations by warping space itself. Then there's the simplest answer: it's just noise. The CMB is a tapestry of tiny fluctuations, and sometimes randomness stacks up in unusual ways. But the cold spot isn't just cold. It's surrounded by a peculiar ring of warmer radiation, a pattern that doesn't fit typical statistical noise. It's this combination, the cold center with its heated halo, that keeps theorists awake at night. The stakes couldn't be higher. If the cold spot is a multiverse fingerprint, it would be the first tangible evidence that our universe isn't alone. It would validate theories like eternal inflation, where new universes constantly sprout from a deeper, invisible reality. But if it's something else, a void, a texture, or just a fluke, it's still a glaring reminder of how much we don't understand about the cosmos's largest structures. For now, the cold spot remains an enigma, a cosmic Rorschach test inviting us to project our boldest theories onto its chilly canvas. Whether it's a window into the multiverse or just a trick of the light, one thing's certain: the universe loves to keep us guessing. And in that uncertainty lies the thrill of discovery, the chance that the next observation, the next dataset, might finally tip the scales toward revelation. Until then, we're left staring at the sky, wondering if that cold patch is a message from beyond or just the universe's way of keeping its secrets a little while longer. Gravity, the force that keeps your feet on the ground and holds galaxies together, has always been treated as one of nature's fundamental pillars, as basic as space and time. But what if it's not fundamental at all? What if gravity isn't a force in its own right, but something that emerges from a deeper layer of reality, like waves rising from the ocean? This radical idea, known as emergent gravity, flips centuries of physics on its head, suggesting that what we call gravity might just be a side effect of how information interacts at the universe's most basic level. The theory's roots stretch back to the holographic principle, which posits that our three-dimensional reality could be a projection of information encoded on a two-dimensional surface. If that sounds mind-bending, here's the kicker. Emergent gravity takes it further. Instead of gravity being woven into space-time like Einstein imagined, it could arise from the way quantum bits of information, tiny pixels of reality, interact with each other. Picture a crowd at a concert. Individual people might move randomly, but the collective motion creates waves that ripple through the crowd. In the same way, gravity might not be a force between masses, but the statistical outcome of countless underlying quantum interactions we can't yet see. This isn't just philosophical musing. Emergent gravity makes a startling prediction. It could eliminate the need for dark matter altogether. In standard physics, galaxies spin so fast that they should fling themselves apart unless invisible matter is providing extra gravity. But emergent gravity suggests that what we attribute to dark matter might actually be a mismatch in our understanding of how gravity scales with distance. At galactic scales, the theory predicts extra gravitational effects without invoking unseen particles. And in 2016, a study of over 30,000 galaxies found their rotation curves matched emergent gravity's predictions as closely as they did dark matter models. The implications are staggering. An entire pillar of modern cosmology might be an illusion, a placeholder for physics we've yet to uncover. Critics, of course, aren't ready to toss out dark matter just yet. They point out that emergent gravity struggles to explain phenomena like the bullet cluster, where colliding galaxies seem to separate their visible matter from their gravitational influence, a hallmark of dark matter's existence. Others argue that without a complete quantum theory of gravity, emergent ideas remain more metaphor than mechanism. But supporters counter that dark matter, after decades of searching, still hasn't been directly detected. Maybe the real mystery isn't what's missing in the universe, but what's missing in our equations. The debate cuts to the heart of how we understand reality. Is gravity a fundamental force, or is it an emergent property, like temperature or pressure, something that only makes sense when you zoom out? If the latter is true, it would mean that space-time itself is a kind of illusion, a collective behavior of something far stranger lurking beneath. And that's the real promise of emergent gravity, not just to solve a single cosmic puzzle, but to reveal a universe where the lines between force, information, and geometry blur into something entirely new. Whether it's right or wrong, one thing's certain: the universe is far more inventive than we give it credit for. And sometimes the most profound discoveries begin by questioning the things we thought we knew best. Crossing the event horizon of a black hole should be a quiet affair, a one-way trip where gravity's pull is so smooth you wouldn't even notice the point of no return. At least that's what Einstein's general relativity predicts. But quantum mechanics paints a far more violent picture. According to some interpretations, the moment you touch a black hole's boundary, you'd be vaporized by an incandescent wall of energy, a firewall of pure radiation blazing at the edge of oblivion. This isn't science fiction. It's a paradox so profound it threatens to unravel our understanding of reality itself. The firewall idea erupts from a clash between two cornerstones of physics. On one hand, relativity insists the event horizon is unremarkable. A passenger falling in would experience nothing unusual, a principle called no drama. On the other, quantum mechanics demands that information can never be destroyed, yet black holes seem to erase whatever falls inside. To resolve this, physicists theorize that black holes slowly leak information back out via Hawking radiation, a faint glow of particles escaping over eons. But here's the catch. For that information to escape, the radiation near the horizon must be entangled with particles deep inside the black hole, and that creates a problem. Quantum entanglement is a delicate bond, a pair of particles sharing a single quantum state, no matter how far apart they are. But the rules say a particle can't be entangled with two things at once. So if Hawking radiation near the horizon is entangled with particles inside, it can't also be entangled with radiation further out. That breaks the entanglement chain, releasing a burst of energy so fierce it would annihilate anything approaching the horizon. Hence the firewall, a cosmic kill switch that preserves quantum rules but turns a black hole's edge into a lethal inferno. The implications are staggering. If firewalls exist, Einstein's smooth spacetime near the horizon shatters. Instead of a silent descent, crossing into a black hole would be like hitting a brick wall of high-energy particles at nearly the speed of light. But this raises another paradox. Observers outside the black hole would see you burn at the horizon, while from your perspective you'd float right through, blissfully unaware. Physics can't have both. One of these cherished theories, relativity or quantum mechanics, must bend. Some physicists argue the firewall is a sign we're missing a deeper truth. Maybe entanglement is more flexible than we thought, or perhaps black holes have hidden structures that resolve the conflict. Others propose radical ideas like ER equals EPR, suggesting entangled particles are connected by microscopic wormholes, weaving spacetime itself from quantum links. Then there's the possibility that firewalls are just illusions, artifacts of how we model quantum information, not real physical barriers. The firewall paradox isn't just about black holes. It's a battleground for unifying gravity and quantum theory, a stress test for the foundations of physics. Every proposed solution forces us to rethink something fundamental: the nature of space, the meaning of information, even the limits of scientific observation. For now, black holes remain the universe's ultimate enforcers, guarding their secrets behind a veil of contradictions. Whether firewalls are real or just mathematical phantoms, they've already done their job, revealing how little we truly understand about the fabric of reality. And that's the real lesson. Sometimes the most destructive ideas are the ones that push us to rebuild physics from the ground up. We've always pictured the universe as an endless, flat expanse, a cosmic stage stretching infinitely in all directions. But what if that's wrong? Cutting-edge measurements of the cosmic microwave background are hinting at a possibility that turns cosmology on its head. Our universe might not be flat or infinite at all. Instead, it could be closed, curving back on itself like the surface of a four-dimensional balloon. If confirmed, this wouldn't just tweak our models, it would rewrite them from the ground up. The clues lie in the way light from the Big Bang's afterglow bends across the cosmos. When scientists analyzed data from the Planck satellite, they noticed something odd. Gravitational lensing distortions in the CMB were stronger than expected, as if space itself were subtly warping the light's path. The most straightforward explanation: a positive curvature to the universe where parallel lines would eventually meet, and a traveler moving far enough in one direction could theoretically return to their starting point without ever turning around. It's a concept straight out of medieval maps, Here Be Dragons. Only this time the edges don't mark uncharted territory, they fold back into themselves. A closed universe flips decades of assumptions. Inflation theory, the dominant model for the universe's expansion, overwhelmingly predicts a flat geometry. So does the standard cosmological model, which aligns with everything from galaxy distributions to dark energy's behavior. But if space curves even slightly, it means we've missed a fundamental feature of reality's architecture. The implications cascade. A finite universe would have a calculable volume, raising wild questions about what, if anything, lies outside. It could also mean the cosmos is destined for a big crunch, where gravity eventually overcomes expansion, pulling everything back into a singularity. Yet the debate is far from settled. Alternative explanations for the Planck data exist, from systematic errors to undiscovered physics at play. Some theorists argue the observed lensing could stem from primordial magnetic fields or even anomalies in how dark matter clusters. Others point out that measurements of baryon acoustic oscillations, the echo of ancient sound waves frozen in galaxy distributions, still strongly favor a flat universe. The tension between these datasets isn't just a minor discrepancy. It's a crisis in cosmology, exposing gaps in our understanding of gravity, dark matter, or perhaps the very nature of spacetime itself. What's at stake isn't just geometry. A closed universe would mean the cosmos is fundamentally interconnected in ways we've barely imagined. Structures on the largest scales could be shaped by topology, with repeating patterns or even ghost images of distant galaxies appearing in multiple directions if space loops back on itself. Time might behave differently in a curved universe, with gravitational waves taking unexpected paths or black holes exhibiting exotic properties. And then there's the philosophical weight. A finite cosmos feels both intimate and unsettling, like realizing you've been living in a snow globe all along. For now, the question remains open literally. New telescopes like the Simons Observatory and next-generation SIMBI experiments are poised to deliver answers with unprecedented precision. Whether they confirm closure or reinforce flatness, one thing's certain: the universe's shape isn't just a trivia question. It's the foundation of everything we know and the key to everything we don't. And if the data keeps pointing toward curvature, we might need to rethink not just where we are, but what where even means. Neutron stars are cosmic monsters, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. They spin at dizzying speeds, some completing hundreds of rotations every second, their surfaces locked in a perfect, rhythmic dance. But every now and then, something bizarre happens. Without warning, these celestial metronomes stutter. Their spins suddenly accelerate just a fraction, but enough to baffle astronomers. These events, called glitches, aren't random malfunctions. They're windows into the most extreme physics laboratory in existence, buried deep within the star's core. At the heart of the mystery lies a substance so strange it defies earthly logic: superfluid neutron soup. Imagine a fluid with zero viscosity, where vortices spin forever without losing energy, and friction simply doesn't exist. This is what neutron star cores are made of, a quantum sea where the rules of classical physics dissolve. Normally, this superfluid rotates in sync with the star's crust, the dense outer shell we observe. But when the two fall out of step, the superfluid's vortices, tiny whirlpools of spinning neutrons, can suddenly reorganize, transferring a burst of angular momentum to the crust like a coiled spring snapping loose. The result, a glitch. The star's spin kicks up as if jolted by an invisible hand. But here's where it gets even weirder. Some neutron stars don't just glitch, they anti-glitch, slowing down inexplicably. Others release energy in tremors, literal starquakes where the crust cracks under unimaginable strain, releasing more energy than a million earthquakes. These quirks hint at layers of complexity we're only beginning to map. The crust itself isn't solid in the way we think. It's a lattice of atomic nuclei crammed so tightly they form bizarre shapes, nuclear pasta. Physicists call it, with structures ranging from spaghetti-like strands to lasagna-like sheets. When this pasta fractures, it might trigger the very vibrations we detect as quakes. The stakes couldn't be higher. Neutron stars are nature's ultimate pressure cookers, squeezing matter into states we can't recreate on Earth. By studying glitches, we're probing the boundaries of quantum mechanics, fluid dynamics, and even the strong nuclear force that holds atoms together. Every unexplained speed up or slowdown is a clue, a whisper from a realm where gravity and quantum weirdness collide, and the implications stretch far beyond neutron stars. If we can decode their behavior, we might unlock secrets about dark matter, which some theories suggest could collect in their cores, or even new states of matter that could rewrite textbooks. These cosmic anomalies aren't just curiosities. They're Rosetta Stones waiting to translate the universe's most extreme language into something we can understand. So the next time a neutron star glitches, remember, it's not a glitch at all. It's the universe nudging us closer to the edge of discovery. Galaxies aren't just drifting apart in the cosmic expansion, some are being pulled. Not by anything we can see, not by any known force in our observable universe, but by something so massive and distant it defies explanation. Astronomers call this enigma the dark flow, a mysterious current sweeping entire clusters of galaxies in the same direction at breakneck speeds, thousands of kilometers per second, as if they're caught in a cosmic undertow. This isn't just random motion, it's a coordinated march towards something beyond the edge of everything we know. The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. As galaxy clusters move, their hot gas scatters CMB photons in a telltale way, imprinting a subtle Doppler shift, a kinematic Sunyaev-Zeldovich effect. When researchers mapped these shifts, they found hundreds of clusters all streaming toward the same patch of sky, toward something unseen. At first, skepticism ran high. Could this be a measurement error, a fluke in the data? But the signal persisted across multiple studies, even when using different instruments. The flow extends billions of light years, far beyond the reach of any known supercluster's gravity. So what's pulling them? One spine-tingling possibility, another universe, not a distant galaxy, not a hidden structure in our cosmos, but a separate space-time entirely, a neighboring bubble in the multiverse, exerting gravitational influence on ours from beyond the veil. Imagine two soap bubbles floating close together. Even if they never touch, their gravity could subtly tug on each other's surfaces. In this scenario, the dark flow might be the first tangible evidence of a cosmos beyond our own, a place where the laws of physics could be utterly alien. But not everyone's ready to jump to multiverse conclusions. Alternative explanations range from colossal, undiscovered voids, regions of space so empty they create gravitational imbalances, to exotic physics like modified gravity or large-scale inhomogeneities left over from inflation. Some theorists argue the flow could be a relic of the universe's pre-inflationary phase, a primordial tug from before space-time smoothed out. Others suggest it's an illusion, a statistical artifact that will vanish with better data. Yet the mystery deepens when you consider the scale. The dark flow isn't just pulling a few galaxies, it's dragging clusters across a quarter of the observable universe, implying a source of unimaginable mass. If it's not another universe, then what could possibly be that massive and lie outside our cosmic horizon? The very idea challenges our definition of the universe itself. Are we looking at the gravitational echo of a long-vanished sibling cosmos, a shadow of something that existed before the Big Bang? For now, the dark flow remains one of cosmology's most tantalizing loose threads. New surveys like the Euclid Space Telescope are poised to map galaxy motions with unprecedented precision, either confirming the flow or revealing it as a cosmic mirage. But either outcome reshapes our understanding. If the flow is real, it's a humbling reminder that our universe might not be the only show in town. And if it's not, well, even false trails lead somewhere, often to discoveries we never saw coming. The dark flow isn't just a mystery, it's a dare to look beyond the edge of the known and ask what else might be out there, tugging at the seams of reality. Every galaxy, every star, every planet, everything we see around us traces back to a moment so fleeting it's almost poetic. In the first sliver of a second after the Big Bang, when the universe was smaller than an atom, quantum fluctuations, those tiny, unpredictable jitters at the heart of reality, left fingerprints on everything. These weren't just microscopic blips, they were cosmic seeds, the blueprints for all structure in the universe. Imagine throwing a handful of sand into a pond. Each grain creates ripples that spread and intersect. Now replace the sand with quantum particles and the pond with the fabric of space-time, those ripples. They're the galaxies we see today. Here's the astonishing part. Those quantum fluctuations didn't just fade into the background. They were stretched, frozen into place by inflation, the universe's explosive growth spurt. What started as subatomic randomness became cosmic unevenness, tiny denser patches where gravity got to work. Over billions of years, those patches pulled in matter, growing into galaxies, clusters, and the vast cosmic web we now observe. The largest structures in existence owe their origins to the smallest possible events. It's as if the universe whispered its plans in quantum code, and we're only now learning to decipher it. But how do we know this isn't just a pretty story? The evidence is etched into the cosmic microwave background, the afterglow of the Big Bang. Satellite maps like Planck's reveal temperature variations, hotspots and cold spots that match the predicted pattern of quantum fluctuations perfectly. The math is breathtakingly precise. The statistical distribution of these variations aligns with quantum theory's predictions down to the tiniest detail. Even the subtle twists in the polarization of this ancient light tell the same tale. A universe built on quantum foundations. This isn't just about the past. It reshapes how we see the cosmos today. Dark matter, that invisible scaffolding holding galaxies together, didn't clump randomly. It followed those primordial quantum ripples, tracing out the cosmic web like ink soaking into pre-drawn lines. Dark energy, the force accelerating expansion, works on a stage set by these same fluctuations. Every time we map a new galaxy cluster or measure the universe's large-scale structure, we're seeing quantum mechanics played out on a canvas billions of light-years wide. The implications run deeper than astronomy. This link between the quantum and the cosmic blurs the line between the very small and the unimaginably large. It suggests that the universe isn't just governed by quantum laws, it's fundamentally quantum at its core. From the birth of stars to the fate of galaxy clusters, everything is connected by a thread of uncertainty, a randomness frozen into fate. And that's the real magic. The universe didn't just arise from chaos. It turned chaos into order, weaving quantum whispers into the tapestry of existence. So the next time you look up at the night sky, remember, Those stars aren't just points of light, they're quantum fluctuations all grown up, and somewhere in their glow is a message from the very beginning, a reminder that the smallest things can shape the grandest designs. The Pioneer spacecraft was supposed to be humanity's silent ambassadors to the star's twin probes launched in the 1970s, destined to drift forever through the void. But as they ventured beyond Saturn, something strange happened. Their trajectories began to deviate ever so slightly from the calculated paths, as if an unseen hand were gently nudging them off course. This tiny but persistent anomaly, just a fraction of a nanometer per second squared in deceleration, baffled scientists for decades. Dubbed the Pioneer anomaly, it became one of space exploration's most tantalizing puzzles. Were we witnessing a glitch in our understanding of gravity itself? At first, the possibilities seemed thrillingly exotic. Could it be evidence of dark matter's gravitational tug in regions we hadn't mapped? Or perhaps a sign that Einstein's general relativity needed tweaking at the scale of the solar system? Some theorists even floated the idea of modified inertia, where the very laws of motion behaved differently in the icy depths of interstellar space. The anomaly became a rallying point for those convinced that our models of physics were incomplete, that somewhere in Pioneer's errant path lay clues to a deeper truth. But science has a way of humbling even the most romantic speculations. After years of painstaking analysis, researchers landed on a far more mundane explanation: heat. Not some cosmic force, but the gentle push of thermal radiation emitted by the probe's own power systems. As Pioneer's plutonium-powered generators decayed, they released heat unevenly, creating a faint but constant recoil that acted like a minuscule thruster. The mystery, it turned out, wasn't a crack in the foundations of physics, just a quirk of engineering we'd overlooked. Yet the Pioneer anomaly's legacy endures, not as a failure of imagination, but as a testament to science's self-correcting nature. It's a reminder that the universe's greatest mysteries often lurk in the smallest discrepancies, the barely perceptible wobbles in the data. And while this particular puzzle was solved, others, like the flyby anomalies of other spacecraft or the subtle orbital quirks of distant objects, still defy explanation. The cosmos is full of such whispers, hints that our understanding is always provisional, always ripe for revision. So the next time a spacecraft veers off course by a hair's breadth, or a star's motion doesn't quite match the equations, pay attention. These aren't just errors to be corrected. They're invitations to look deeper, question harder, and remember that even in the age of precision astronomy, the universe still has surprises up its sleeve. And that's the real lesson of the Pioneer anomaly. Sometimes the smallest deviations point to the biggest truths. The vacuum of space isn't empty, not even close. Quantum physics tells us it's a seething, bubbling froth of virtual particles popping in and out of existence, each flicker contributing to what we call vacuum energy. This energy should be enormous. Theoretical calculations put its density at a staggering 10 to the power of 112 joules per cubic meter. That's enough to rip space-time apart instantly. Yet when we measure the actual energy driving the universe's expansion, dark energy, it's almost laughably small, just 1 joule per cubic meter. That's a discrepancy of 120 orders of magnitude, a number so vast it's like comparing the size of a single atom to the entire observable universe. This isn't just a gap in our knowledge, it's the most embarrassing mismatch between theory and observation in the history of science. Welcome to the Vacuum Catastrophe. So why does this matter? Because vacuum energy isn't some abstract curiosity, it's the very fabric of reality. Every cubic centimeter of so-called empty space crackles with this energy, and according to Einstein, it should warp spacetime with unimaginable force. Yet the universe isn't torn to shreds. Instead, dark energy's gentle push is just strong enough to accelerate cosmic expansion without destroying everything. This absurd fine-tuning suggests one of two possibilities. Either our theories of quantum fields are catastrophically wrong, or there's a hidden mechanism cancelling out almost, but not quite, all of this energy. The leading suspect, supersymmetry. This elegant theory posits that every particle has a superpartner, balancing the quantum book so perfectly that vacuum energy nearly zeroes out. But here's the catch. If supersymmetry exists, we should have detected these particles by now. The Large Hadron Collider's silence has left physicists scrambling. Alternatives abound, from extra dimensions bleeding off energy into hidden realms to the controversial idea that vacuum energy isn't constant at all. It's a decaying field that just happens to look constant in our cosmic epoch. Then there's the radical notion that we're asking the wrong question entirely. What if vacuum energy doesn't gravitate the way we think? Some theories suggest gravity might see this energy differently, effectively filtering out its monstrous theoretical value. Others propose an anthropic explanation. In a multiverse where vacuum energy varies randomly, we inevitably find ourselves in a rare universe where it's survivably small. The Vacuum Catastrophe isn't just a puzzle, it's a flashing neon sign pointing to where our theories break down. Solving it could require rewriting quantum mechanics, reimagining gravity, or uncovering entirely new physics. And that's the real stakes here. Hidden in this worst prediction in science might be the key to the universe's deepest secrets. The next breakthrough won't just fix a calculation, it could reveal the missing piece that unites all of physics. Until then, the vacuum keeps its secrets humming quietly beneath the surface of everything. Deep in the constellation Aradana lies one of the universe's most unsettling enigmas, a cavern of nothingness so vast it could swallow thousands of galaxies whole. This is the Aradana Supervoid, a region of space stretching nearly 2 billion light-years across where matter is strangely, inexplicably sparse. It's not just empty, it's too empty, a cosmic desert that defies the universe's usual clumpiness. And here's where it gets eerie. This void lines up almost perfectly with the CMB cold spot, that mysterious cold patch in the afterglow of the Big Bang. Coincidence, or could this sprawling nothingness be actively stealing energy from light, leaving behind a chill in the cosmic microwave background? The physics behind this is as elegant as it is bizarre. When light travels through the universe, it gains or loses energy depending on the terrain. Pass through a dense galaxy cluster, and gravity's pull gives photons a boost, a process called the Sachs-Wolf effect. But enter a supervoid and the opposite happens. Photons expend energy climbing out of this gravitational valley, stretching into longer, cooler wavelengths. The Aradana supervoid is so colossal that the cumulative effect could explain the cold spot's temperature dip. It's like rolling a marble down a hill, except the hill is a billion light-years wide, and the marble is ancient light from the dawn of time. But not everyone's convinced. The sheer scale of the void is a problem. According to standard cosmology, structures this large shouldn't exist. The universe simply hasn't had enough time to evolve such a gaping hole. Some simulations suggest the odds of a void this size forming naturally are less than 1 in a million. That's led to wilder theories. Perhaps the supervoid is a scar from an ancient cosmic collision, a bubble of deflated spacetime left over from before the Big Bang. Others propose it's evidence of a cosmic texture, a defect in the fabric of reality formed when the early universe underwent a phase transition, like ice cracking as it freezes. Then there's the statistical counterargument. Maybe the alignment between the void and the cold spot is just a fluke. the universe is vast and improbable things happen. Yet the more we study the void, the stranger it gets. Galaxy surveys show its edges are unusually sharp, as if carved by something deliberate, and the cold spot itself has a peculiar ring of warmer radiation around it, a pattern that doesn't quite fit the void explanation alone. It's as if the universe is teasing us, dangling clues but refusing to reveal the full picture. What's at stake isn't just one anomaly. If the supervoid is real and linked to the cold spot, it could mean our models of cosmic structure formation are missing a crucial piece. Or worse, that we've misunderstood gravity itself on the largest scales. Dark energy's behavior, the growth of filaments in the cosmic web, even the fate of the universe could all look different if voids like Aradana are more than cosmic accidents. For now, the supervoid remains a ghost in the data, a shadow that might reshape cosmology or fade into statistical noise, but that's the thrill of the hunt. Every anomaly, every outlier is a chance to peek behind the curtain of reality and ask, what if we've been missing something monumental? The Aradana supervoid isn't just a hole in space. It's a window into the unknown, and the view from the edge is anything but empty. Hidden beneath the familiar four dimensions of space-time lies a mathematical jewel so intricate it could rewrite physics, the E8 lattice. Picture an 8-dimensional snowflake, its symmetry so perfect that every point connects to others in a dance of geometric harmony. This isn't just abstract art. Some physicists believe this structure might be the master key to the universe, encoding every known force and particle in its dazzling complexity. The idea is audacious. What if gravity, electromagnetism, and even the quirky quantum behaviors of particles are just shadows cast by this higher dimensional shape? The E8 theory traces its roots to a bold proposal by physicist Garrett Lissy, who noticed eerie parallels between the lattice's symmetries and the standard model's particle zoo. In this framework, an electron's spin or a photon's polarization isn't just a property, it's a direction in an 8-dimensional space, a twist or turn in the E8's labyrinthine geometry. Even the Higgs boson, the particle that gives others mass, slots neatly into the pattern like a missing puzzle piece. The allure is undeniable. Instead of stitching together disparate theories, E8 offers a single, unified tapestry where everything fits. But here's where it gets thorny. For all its elegance, E8 struggles to explain gravity's place in the quantum realm. String theory, the reigning contender for a theory of everything, requires 10 or 11 dimensions and a menagerie of vibrating strings. E8, by contrast, is minimalist. Its power lies in doing more with less. Yet critics argue it lacks the machinery to describe how gravity emerges at quantum scales, a hurdle even its supporters admit is formidable. The math is breathtaking, but does it describe reality or just a beautiful mirage? The debate isn't just academic. If E8 is correct, it would mean the universe's deepest truths aren't equations but shapes geometry woven into the fabric of existence. Experiments could test its predictions, like uncovering new particles corresponding to undiscovered symmetries in the lattice. Others hunt for subtle quantum gravity effects that might betray E8's influence. And even if it falls short, the theory's boldness has already inspired new ways to think about unification, proving that sometimes the wildest ideas are the ones that push science forward. So why does E8 captivate? Because it dares to imagine a universe where beauty and truth are one, where the messiness of physics resolves into crystalline symmetry. Whether it's the final answer or just a stepping stone, E8 reminds us that the cosmos might be simpler and stranger than we ever dreamed, and in that possibility lies the real magic, the chance that the next great breakthrough won't come from a thicker textbook but from a deeper dimension. Standing in your backyard at night, you might notice the planets tracing a neat path across the sky, the ecliptic plane, where our solar system's orbits align like grooves on a vinyl record. But zoom out to the scale of the cosmos, and this tidy arrangement becomes bizarrely peculiar. Our solar system's plane isn't just tilted relative to the Milky Way, it's also aligned at an unsettlingly precise angle with the cosmic microwave background, the afterglow of the Big Bang itself. This isn't just a random quirk. The odds of such an alignment happening by chance are less than 1 in 1,000, raising a spine-tingling question. Could this be a fossilized imprint from before the Big Bang? A cosmic handshake between our local structure and the universe's very origins. The CMB isn't just thermal noise, it's a snapshot of the infant universe, its temperature variations revealing the seeds of all future structure. And here's the twist, the hottest and coldest spots in this primordial light aren't scattered randomly. They're arranged in patterns that eerily mirror our solar system's orientation. It's as if the universe's birth left behind a subtle coordinate system, and for reasons we can't yet explain, our planetary neighborhood decided to follow its lead. Some theorists argue this can't be coincidence, that it hints at a deeper connection between local and cosmic physics, a symmetry woven into space-time itself. One provocative explanation dips into speculative cosmology, conformal cyclic cosmology, a theory proposing that the Big Bang wasn't a true beginning but a transition from a prior universe's death. In this model, information from that earlier epoch could have imprinted itself on the CMB, leaving behind faint directional clues. Our solar system's alignment might then be a cosmic inheritance, a subtle echo of physics operating across eons. Others suggest this could be evidence of a multiverse, where neighboring universes exert gravitational nudges on one another during inflation, leaving behind telltale anisotropies. But skepticism abounds. Could this just be a classic case of apophenia, our brains imposing patterns on randomness? After all, if you stare at any dataset long enough, you'll find something that seems significant. Yet the statistical unlikelihood keeps pulling scientists back. Some have proposed more mundane explanations, like undiscovered local foregrounds contaminating the CMB data, or peculiarities in how our galaxy's motion affects measurements. But each time researchers account for these factors, the anomaly stubbornly persists. What's at stake isn't just a curiosity, it's a potential crack in our understanding of cosmic causality. If the ecliptic alignment is real, it challenges the cosmological principle, the bedrock idea that the universe is homogeneous and isotropic on large scales. It would mean our corner of reality isn't just a passive observer, but strangely entangled with the universe's deepest architecture. Future CMB experiments, like next-generation space telescopes, aim to settle the debate with sharper data. Until then, the ecliptic anomaly remains a tantalizing what if, a whisper that the universe's origins might be far more textured and far stranger than we ever imagined. So the next time you gaze at the planets arcing across the night sky, remember, you're not just seeing orbits, you're looking at a cosmic mystery, a riddle written in gravity and light, waiting for its solver. Black holes have long been the universe's ultimate enigmas, cosmic vacuum cleaners, sucking in everything that crosses their event horizons. But what if these gravitational monsters aren't just destroyers? What if they're the invisible architects of the cosmos itself? A radical idea is gaining traction. Dark matter, that elusive substance holding galaxies together, might not be made of exotic particles at all. Instead, it could be a sea of ancient black holes, forged in the chaos of the Big Bang and lurking unseen in the cosmic shadows. This isn't just wild speculation. Gravitational wave observatories like LIGO have detected collisions between black holes with masses that don't fit the standard stellar model, too heavy to form from collapsing stars, yet too light to be supermassive giants. These oddballs, some weighing in at tens of solar masses, line up eerily well with predictions for primordial black holes, hypothetical relics born from density fluctuations in the universe's first moments. If these black holes exist in vast numbers, they could solve two mysteries at once: the nature of dark matter and the origin of these puzzling gravitational wave signals. Imagine the early universe as a bubbling cauldron of energy, where pockets of space momentarily collapsed under their own weight, pinching off into black holes without the need for stars to die. These primordial black holes wouldn't glow or accrete matter like their stellar counterparts. They'd be nearly invisible, drifting through galaxies like ghosts. And here's the kicker: if they're small enough, many could have evaporated by now via Hawking radiation, leaving behind only the heaviest survivors, perfect candidates for the dark matter we've been chasing. The beauty of this idea lies in its simplicity. No new particles, no undiscovered forces, just gravity, warping space in ways we already understand. Dark matter's gravitational effects, from the rotation curves of galaxies to the bending of light around galaxy clusters, could all be explained by swarms of these ancient black holes. Even the cosmic web, that vast network of filaments connecting galaxies, might trace back to their gravitational influence, but the theory isn't without hurdles. If primordial black holes are everywhere, why haven't we seen more microlensing events, brief brightenings of stars when a black hole passes in front? Some models suggest they could be clustered in halos around galaxies, avoiding dense stellar regions where such events are easier to spot. Others propose they're hiding in the voids between galaxies, their gravity subtly shaping the large-scale structure of the cosmos. The stakes couldn't be higher. If this connection holds, it would mean dark matter isn't some exotic substance but a population of black holes woven into the universe's fabric from the very beginning. It would also rewrite the story of cosmic evolution, suggesting black holes played a starring role in shaping galaxies long before the first stars flickered to life. For now, the hunt is on. Telescopes are scouring the skies for the telltale flickers of black holes lensing distant stars, while gravitational wave detectors listen for the whispers of more collisions. Each new signal could be the clue that cracks the case or the anomaly that sends theorists back to the drawing board. One thing's certain: if dark matter is made of black holes, the universe just got a lot darker, a lot stranger, and infinitely more fascinating. Physics has always relied on one unshakable assumption: the laws of nature are eternal. The numbers we plug into our equations, the speed of light, the charge of an electron, the strength of gravity, are supposed to be fixed, unchanging threads in the fabric of reality. But what if we're wrong? Hidden in the light of distant quasars, there's a whisper that one of these fundamental constants might be shifting over time. The fine structure constant, a number that governs how light and matter interact, appears to be playing by different rules in different corners of the universe. This isn't just a minor tweak to physics, it's a potential earthquake threatening to crack the foundations of everything we know. The fine structure constant, often denoted by the Greek letter alpha, is a peculiar blend of nature's most basic ingredients: the charge of an electron, the speed of light, and Planck's constant. Together, they determine how tightly electrons cling to atoms and how strongly light interacts with matter. For decades, we've treated alpha as inviolable, a cosmic keystone holding the periodic table together. But when astronomers analyzed the spectra of quasars, ancient galaxies, whose light has traveled billions of years to reach us, they noticed something unsettling. The absorption lines in that light, which act like fingerprints for atomic elements, didn't quite match what we see in labs today, the only explanation. Alpha might have been slightly smaller when those photons began their journey. Now, a change of 1 part in 100,000 over 10 billion years might not sound dramatic, but in the world of fundamental constants, it's apocalyptic. If alpha varies, it means the universe's rulebook isn't written in permanent ink. The strength of chemical bonds, the colors emitted by stars, even the stability of matter itself could all drift over cosmic time. The implications ripple outward. Maybe other constants aren't so constant either. Could the speed of light have been different in the past? Might gravity's pull weaken over eons? Suddenly, the bedrock of physics feels like shifting sand. The debate over these measurements is fierce. Some teams claim the variations are statistical flukes, artifacts of how we interpret quasar spectra or calibrate telescopes. Others argue the signal is real but localized, hinting at exotic physics where constants behave differently in different regions of space, a concept that would make Einstein's head spin. Then there's the wildest possibility, that alpha's drift is evidence of extra dimensions, places where the fabric of reality is warped in ways we can't directly see, but that subtly tweak our laws from afar. For now, the question remains open. Next-generation telescopes and atomic clocks precise enough to detect tiny drifts over decades are joining the hunt. Whether alpha's variability holds up or not, the mere possibility has already done something remarkable. It's forced us to confront the uncomfortable idea that the universe might not be as predictable as we thought. The constants we've always taken for granted could be cosmic variables quietly evolving as the ages pass. And if that's true, we're not just decoding the universe's laws, we're watching them rewrite themselves in real time. What if the universe isn't just something we observe? What if it's something we create through the act of observation itself? At the heart of quantum mechanics lies a peculiar idea. Particles don't settle into definite states until they're measured. Electrons exist as probability clouds, photons behave as both waves and particles, and the very act of looking seems to force reality to make up its mind. This observer effect has sparked a radical fringe theory that consciousness isn't just a passive witness to the cosmos, but an active participant in shaping it. It's a notion that blurs the line between mind and matter, suggesting the universe might not exist as we know it without someone or something to perceive it. Take the famous double-slit experiment, where particles fired at a barrier with 2 openings create an interference pattern, as if they're waves spreading out and overlapping. But the moment scientists place a detector to see which slit each particle passes through, the wave-like behavior collapses. The particles start acting like discrete bullets, as if they know they're being watched. This isn't just a quirk of microscopic physics. Some interpretations, like the von Neumann-Wigner hypothesis, take it a step further, proposing that consciousness itself is the trigger that collapses quantum probabilities into concrete reality. In other words, the universe might be a vast, shimmering quantum soup until a conscious observer stirs it into shape. Critics dismiss this as metaphysical speculation, arguing that observation in quantum mechanics refers to interactions with any measuring device, not necessarily a conscious mind. Yet the mystery deepens when you consider the scale of the cosmos. If consciousness plays a role in reality's structure, could the universe have evolved differently without observers? The Anthropic Principle hints at this, noting how eerily fine-tuned the laws of physics are for life to exist. But the consciousness-cosmology link goes further. It suggests that life, and perhaps even intelligence, isn't just an accident of physics, but a necessary ingredient for the universe to fully manifest. Then there's the hard problem of consciousness itself, why subjective experience exists at all. If the brain is just atoms obeying physical laws, where does the inner world of thoughts and sensations come from? Some theories, like panpsychism, propose that consciousness is fundamental, woven into the fabric of reality at the smallest scales. In this view, even particles might possess a rudimentary form of awareness, and complex minds like ours arise from the collective hum of these tiny sparks. It's a controversial idea, but one that bridges the gap between quantum weirdness and the palpable solidity of the world we perceive. The implications are dizzying. If consciousness and cosmos are intertwined, then the universe might not be a cold, indifferent machine, but a dynamic interplay between observation and existence. It would mean that every time you look at the stars, you're not just seeing light from distant suns, you're completing a circuit that stretches back to the Big Bang, a cosmic dance where perceiver and perceived are partners. Skeptics will demand proof, and rightly so, but in a universe where the act of looking changes what's seen, perhaps the real question isn't whether consciousness shapes reality, but how deep the connection goes. And that's a mystery not just for physicists, but for anyone who's ever wondered why there's something rather than nothing. The universe is playing a cosmic game of tug-of-war, and the outcome will determine everything, whether galaxies continue drifting apart forever, collapse back into a fiery singularity, or cycle through endless rebirths like a cosmic phoenix. Right now, dark energy is winning, pushing galaxies apart at an accelerating pace. But is this the final word? The universe's fate hinges on a delicate balance between expansion and gravity, between the push of dark energy and the pull of matter. And the possibilities are as dramatic as they are uncertain. Picture a campfire slowly burning down to embers. That's the heat-death scenario, a future where dark energy keeps stretching space-time until every star burns out, every black hole evaporates, and the cosmos becomes a vast, silent graveyard of near-absolute zero. No new structures form, no energy flows, just a faint whisper of leftover radiation, fading into oblivion over trillions upon trillions of years. It's a lonely ending, but it's the leading prediction if dark energy remains constant, as the cosmological constant suggests. But dark energy might not play fair. What if it strengthens over time, growing more potent as the universe expands? In this nightmare scenario called the Big Rip, galaxies wouldn't just drift apart, they'd be torn to shreds. Stars, planets, even atomic nuclei would be ripped apart by the runaway expansion of space itself. The universe wouldn't just die, it would unravel at the seams. Then there's the opposite possibility, a big crunch. If dark energy weakens or reverses, gravity could finally gain the upper hand. Galaxies would slow their flight, then fall back toward each other in a cosmic reversal. Space would contract, temperatures would soar, and everything would collapse into a singularity, perhaps igniting a new Big Bang. This cyclical model, where universes bounce from expansion to contraction, suggests our cosmos might just be one link in an infinite chain. But the wildest idea of all, that the universe isn't heading toward any single fate, but branching into multiple realities. Quantum fluctuations, inflationary bubbles, or even black hole births could spawn new universes with their own laws, their own timelines, their own destinies. In this multiverse scenario, our universe's end might just be a footnote in an infinite tapestry of cosmic stories. For now, the answer remains hidden in the behavior of dark energy, a force we've barely begun to understand. Every observation, every telescope pointed at distant supernova or the cosmic microwave background brings us closer to solving the ultimate cosmic cliffhanger. Will the universe fade, collapse, or rebirth itself? The uncertainty isn't frustrating, it's exhilarating, because in that mystery lies the universe's final, greatest secret. From quantum foam to cosmic webs, these 38 insights paint a universe far stranger and more magnificent than we ever imagined, a reality where empty space crackles with hidden energy, where time might be an illusion, and where the very laws of physics could be shifting beneath our feet. Every discovery, from the coldest corners of the cosmic microwave background to the fiery hearts of colliding black holes, peels back another layer of reality, revealing just how much we've yet to understand. The cosmos refuses to fit neatly into our textbooks. It dances at the edges of our comprehension, always one step ahead. And that's the real magic, not just the answers we've found, but the questions that keep multiplying. Why does the universe have a preferred axis? What lurks beyond the great attractor's pull? Are we alone, or is the silence itself a clue? Each mystery is a doorway, inviting us to rethink everything we thought we knew. Technology is our torch in this endless cave of wonders. Gravitational wave detectors listening to spacetime's ripples, quantum computers simulating alternate realities, telescopes peering back to the first flickers of light. With every tool we build, the universe reveals a little more, not just its secrets, but its sense of humor, its contradictions, its willingness to surprise us. Yet for all our progress, the night sky remains the same awe-inspiring canvas it's always been. Those pinpricks of light aren't just distant suns, they're reminders that curiosity is humanity's superpower. We're the universe observing itself, unraveling its own riddles one insight at a time. So whether you're drawn to the elegance of emergent gravity or the enigma of dark flow, remember, the greatest discoveries often begin with a simple, childlike wonder. What's out there? How does it work? And what does it mean for our place in the grand scheme? The journey is far from over. New theories will rise, old ones will fall, and the cosmos will keep challenging us to think bigger. But one thing's certain, the more we learn, the more breathtaking the story becomes. So look up tonight. Somewhere in that vast expanse, a mystery is waiting not just for scientists, but for anyone daring enough to ask, what if? The universe is talking. Are you listening? Drop your favorite insight in the comments and let's keep exploring together. The next revelation, it's already